Good morning. So today we are going to look at some pre-modern economies. So how to understand stagnation in a more detailed and methodic manner. For this purpose, we are basically looking at a paper by Lucas. So this is in the 2002 textbook. So there is this book, Lectures on Economic Growth, where he collects all the papers he wrote on growth, plus this additional paper that studies some Malthusian economies, all right? So all of these models will have a Malthusian logic. And in some of them, we're gonna look at hunter-gatherer societies. And also we're gonna look at societies of agriculture where there could be two different classes, right? Two different social classes. So one will be workers and the other will be, of course, landowners, okay? Now the important conceptual tool here that we're gonna exploit is the dynastic preferences. All right, so you are familiar with this actually, I think from our mathematical economics class, because if people care not only for themselves, but also for their kids, right? So then their problem is essentially a dynamic problem. And here in this lecture, we're gonna look at models where adult people, one generation of adults, will have particular preferences that also account for their kids' welfare, right? So then the problem becomes, the utility function becomes a forward-looking kind of utility function. And in such a case, of course, optimality requires how to optimally accumulate your resources. So here, that particular resource will be land, okay? So another important aspect, of course, since these are all Malthusian economies, of course, fertility is endogenous, right? So there's a return to fertility and there's a cost to fertility, and people are maximizing their welfare through this. So.
Pardon hocam, bir şey sorabilir miyim?
Evet.
Hangi makale demiştiniz hocam bu?
Lucas 2002. So this is a book, Lectures on Economic Growth. In this book, the particular chapter is, I think, chapter 5 or chapter 6, perhaps. Past and present. The title is Past and Present.
Okay.
Okay.
Thank you.
You're welcome. So let me show you what these dynastic preferences are. So we're going to look at discrete time models. Here, the length of a period is rather long, right? Maybe 25 years, 20 years, 30 years. So it basically covers the entire, childhood episode and entire adulthood episode, okay? And there are two overlapping generations, adults and children. So people are going to be born at some point, and then they're going to live a life as a child. Then in the second period of life, they're going to become adults. Okay, reproduction is asexual. So there's no difference between males and females. This is a huge simplification. There are models where you can write, you can differentiate males and females. But for now, for our purposes now, it is not really important. So each adult in the beginning of her adulthood gives birth to n children. Okay, so n is fertility. Okay. Now, when we say dynastic preferences, we're going to be, of course, specific with the generation, right? So generation T adult, this is an individual. So this individual will have a utility function. Okay, this utility function is W. So it depends on three things. CT is the consumption. Okay, so there's a final good. That final good is consumed by the adult. So that consumption level gives a utility to the adult. And then there is fertility level. So people like to have kids, as typical in these models, right? So the number of kids they have gives utility. And finally, the welfare of their children, okay? So here we're gonna be more specific in a couple of moments, in a moment, but basically we are taking that, okay, this utility is common across children, right? So this common utility level of generation T plus 1 is an argument in the utility of generation T. Okay, so this is altruism basically. So this type of preference is called dynastic preferences by Lucas. Why? Because as you see, there's a dynasty here, right? My kids. So if I am a generation T adult, my kids will be generation T plus 1, and they also face this similar utility function, right? Their utility UT plus 1 will depend on W CT plus 1, their number of kids, and T plus 1, and their kids' welfare, my grandkids' welfare, right? UT plus 2. So, and that goes on. That's the notion of dynastic preferences. Now, in the models today, we're going to be more specific about the utility function because we're going to do some analytical solutions. So here, the function is logarithmic. Okay, so you may imagine that there's a side that depends on current utility. The other side depends on current consumption. The other side depends on current fertility. And you also have this, of course, discounting term, right? So here, altruism is kind of mixed with discounting, right? So I care about my kids and their utility eventually, as you see, defined as a Bellman equation, right? So you may imagine that this is the value function, okay? If you maximize this by choosing consumption optimally and fertility optimally, then this is just the Bellman equation, all right?
Sorry, adults will die in the next period.
Yes.
T plus 1.
Yes. So the logic is this: at the beginning of T, I enter my adulthood, right? At the end of T, I die as an adult, and my kids enter their adulthood. Okay.
Okay.
So, of course, we can imagine UT plus 1 as the quality of children, right? So there's still a quality quantity trade-off in this model because in some versions of this theory, actually, you can increase your kids' welfare through education, for instance, right? And so on and so forth. So, but here today, when we try to understand hunter-gatherer societies and two-class agricultural societies or feudal societies, we're going to look at this utility function. Now, let's start with the hunter-gatherers, okay? So time is discrete again, And there are anti-dynasties, all right? So this means each adult has its own dynasty, right? So whenever there's a kid born, there will be a dynasty with that. So you may replace the word dynasty with family as well, all right? So at the beginning of T, then there are anti-adult individuals. Okay. Now each of them has 1 unit of labor. Okay, so this is of course normalized, and we also assume that the economy has a given level of resources. Okay, L. So this could be land. When in a hunter-gatherer society, when we say land, we basically mean all the animals that can be hunted, all the vegetables or fruits that can be gathered and enjoyed, right? But this is fixed. That's the idea of resources here. So they cannot be cultivated, right? And again, we have the utility function, right? So that's also typical. Now there is a production technology, of course. Now in the hunter-gatherer society, the production technology is basically you go to the nature, you collect the stuff, you hunt the stuff, and you eat it, right? But still, we can talk about a production technology, right? Why? Because there's this land, and then you have to go there and do the work, all right? Do the hunting, do the gathering. So this allows us to define the typical constant returns to scale production function, all right? And one particular example is this, what you see here at the last line, right? So there's this fixed productivity, and X is land per capita, right? There's no physical capital, of course, in such a primitive society. I mean, you may imagine that they have arrows and they have swords and all the things, but they all can be accounted within this A parameter, right? So basically, it is stagnating, right? There's no advance in technology. So we look at a hunter-gatherer society within one particular technological paradigm, right? So there's no technological change within the episode we are looking at. But if the production function exhibits constant returns to scale, then I can write the production at per worker level, right? Or per capita level. So then this also means, of course, per dynasty level. Then we have YT, which is equal to lowercase f of xt. And again, I write this function as a to the xt to the alpha, a times xt to the alpha, right? So alpha is between 0 and 1 because the function f exhibits constant returns to scale, so alpha remains there, as you know. Now, there is another technology, the technology of reproduction, of course, right? So how to make kids? So what is the cost of fertility, right? So we already understood the return of it. So there's this argument in the utility function that depends on the number of kids. But what is the cost, right? So here, the cost will be in terms of the final good, right? So your kids will also consume some stuff, all right? So you have to feed them, you have to protect them, etc. So the simplest possible case, of course, is to assume that there is a fixed cost associated with each kid. So K could be the units of the final good each kid consumes, right? So then the budget constraint, of course, is this, right? So that my income in a hunter-gatherer society is the average product I have. So this society is entirely, as you know, egalitarian. There could be, luck involved. Some people are skill level differences are important, perhaps. So some people are better hunters, some people are better gatherers. But overall, to understand the macro level phenomena, we can write that consumption plus what your kids consume must be equal to what you obtain from the nature, right? So then you have this budget constraint. Then the problem is very simple, right? Why? Because land is not owned. Land is not a part of private property. In fact, there is no private property in this hunter-gatherer society. The logic of hunting and gathering is that you, as the community, you first enjoy living in a particular place. There are resources there, and you exploit these resources for your consumption. And then at some point, you may leave for another place, right? Once the resources there are no longer available, or for other reasons, maybe there's a climate catastrophe, maybe there's a war, maybe there's some sort of some other type of problem that forces these people to move another place, right? So the entire notion of private ownership does not really make sense for these hunter-gatherers. So land is not owned, so land is nobody's, right? This means the problem is not really dynamic for the hunter-gatherers, right? Why? Because they only can choose consumption and fertility. Even if they care about the kids' utility, they have no vehicle to affect their kids' utility, right? So in the simplest possible case, then the solution to this problem can be expressed, can be described by this first order condition, okay? So you replace consumption using the budget constraint, then take the derivative with respect to fertility, and you find this. Now realize that, of course, when I say there is no vehicle for the adults to affect their kids' utility, this means there is no state variable, right? That allows people to trade off resources from two different periods, right? So the entire notion of dynamic programming, as you know from your mathematical economy classes, is to transfer resources from today to the future, right? Today to the tomorrow. So here there is no such state variable. There's no physical capital. There is no land that is owned privately. So the result is that, yes, I care about my kids' utility, but I cannot affect it. My kids will be on their own, in the nature, in their adulthood. Okay. So once you solve this for a steady state, right? So once you solve this equation for a steady state, so we are interested in a steady state, all right? So why is that? Because the entire study of dynamic paths require, of course, dynamic programming techniques, numerical techniques. We are not really interested in them for this class. What we are after is to understand Malthusian steady states, long run phenomena, right? So for this reason, we are looking at a steady state where adult population is fixed, right? So population is fixed, basically. How can population be fixed in such an economy? Well, if everybody has one kid, right? Each kid replaces the parent, then population remains constant. Okay, so we are looking at steady states that satisfy this property. All right, but this also implies in the steady state, there will be no change in output per worker, no change in consumption per worker, and no change in utility. Okay? So from this equation, we already know that n equals 1 is the steady state, right? Net fertility is equal to 1. So using this equation, you can solve for subsistence income. Okay? Why it is called subsistence? Because if they have more resources in this economy, they will have more kids, right? So in this sense, this economy is strongly Malthusian. Okay? This economy is strongly Malthusian. So let's look at the determinants of this subsistence level of income. Well, if they put more emphasis on consumption, okay, 1 minus beta is the parameter that determines the marginal utility of consumption as opposed to fertility, right? So this increases subsistence income. Eta is the parameter that mainly determines the marginal cost of fertility, marginal utility of fertility. So that decreases subsistence income because more weight again is given to the consumption relatively. And there's K here, right? So what was K? Remember, K was the cost per unit, so the unit cost of fertility. So if this cost is larger, okay, if kids consume more calories in this society, okay, then subsistence income is also larger. Why? Because you are required to have more resources, okay, to sustain a given level of population. So it is in this sense subsistence. Why? Because if income is lower than that, then you cannot sustain fertility that is equal to 1, right? So if you solve this equation, you understand that Y, income Y, is the minimum level of income that you need to have at least 1 kid, right? So if you have an income lower than this level for some reason, then you cannot sustain to have more than 1 kid. Now, obviously, in the short run, this depends on all the technology and land you have, but in the long run, this is the important Malthusian feature. In the long run, it does not depend on technology. It does not depend on resources, okay? In the long run, it depends on your preferences and the cost of fertility, okay? So that's a very important Malthusian feature. So technology, land endowment, sophistication of your production techniques, and all the other stuff that you may once imagine affecting the income level in the long run does not matter at all because of the Malthusian checks, okay? So that's it. Now, of course, you can write consumption, right, using the budget constraint, because now you have Y, you have the budget constraint. So consumption, subsistence consumption is equal to this, okay? Then finally, you can use a production technology to find land per capita, okay? And this is that, right? So you basically solve for X. And as you see, land per capita, of course, depend on technology and production function parameter. All right? Why? Because population adjusts to these things. Remember that, maybe I can use my whiteboard, just a sec. So if you think about this,
Sorry, your voice is not clear.
what about now?
Okay, good.
It's okay now? All right. So remember that X is this, right? Length per worker. So L is given and N is endogenous. Okay? So once you find X star, let's say, right? So this is, let's say, X star. So you can denote the steady states by stars. Okay? Once you have that, realize you can write this, right? And star is equal to L divided by X star. Okay? And if you do that, you realize steady state population level is increasing in technology, right? So once you have a technological advance, let's say a one-time increase in technology A, then in the long run, this will be translated into more population, okay? And in fact, a higher population density, right? So what is population density here? It is 1 over X, right? Population density is 1 over X. If you think of L as the physical size of the land, right? So then we have the typical Malthusian features. Let me summarize. Malthusian incomes are independent of technology in the long run. And the impact of technology in the long run will be observed only in population. So this explains why the Roman Empire, Ottoman Empire, Chinese Empire have larger populations than, you know, all the other small empires, small states. So there are large population differences, right? But their income level is similar. And in fact, in modern standards, it is around 550 to 600 US dollars in terms of 2011 US dollars. Okay, so if you look at Angus Madison's website, Angus Madison's database, you realize that there's this huge collection of pre-industrial income estimates, and those estimates are all similar. Why? Possibly because those economies were subject to Malthusian constraints. Okay? So, what else we have for this? Yes. So now you can also calculate steady state utility, right? How do you do that? Well, you go to the utility function, right? So basically, you have let me show you. So basically, you have U equals 1 minus beta ln C, right? Eta ln N plus beta U. So U is equal to 1 minus beta ln C plus eta ln N divided by 1 minus beta, right? So N is already equal to 1. C is equal to 1 minus beta eta K. So if you put these into that, you're going to find U as a function of parameters. Okay? And of course, it will be depending on the subsistence consumption level. Okay? So let me clear all of this. Oops. All right. Now, we're going to look at another type of society, the same technology, same preferences. Okay, same technology, that's important. Same technology, same preferences. But now, we're going to let people to own the land. All right, so this will be now an economy after Neolithic revolution, let's say. So people know how to domesticate plants, how to domesticate animals, so they can have full control over over the nature in that particular sense. And with private ownership of land, you will realize people will use land as the state variable that will transfer their resources to the future generations. Okay? Now, this implies the problem becomes a regular dynamic programming problem, right? Because if I want to have my kids also attain a sort of, let's say, optimal utility, which is this, right? Vxt plus 1. Then I have to be careful when I'm choosing my fertility. Why? Because remember, xt was land endowment divided by population, right? What is xt plus 1? Well, xt plus 1 is this. What do I know about population? Well, population grows through this equation, right? So I have the transition equation, right? If I have more kids, then I leave lower units of land to my kids. If I have more land, I will leave more. All right? So now, be careful though, we are still looking at a classless society. Okay? And we are assuming that every member of a generation, so suppose that these are members of the generation, right? Or you can actually use this. Okay. So every member of the generation are identical. So we basically assume that there's no heterogeneity. Okay. So if you want to study inequality across people, we can of course do that. So each would have a particular welfare function, a particular fertility level, a particular income. So you can actually differentiate technology as well. So income will be different. So you can do all of these things. But for now, it's all really not necessary to understand the particular things that we want to understand. So the problem is very similar to what you saw earlier in your math classes. So there is this initial value. Initially, there's a land endowment, and this defines land per family or land per dynasty, right? So there is the production technology, the same production technology we had earlier, and then there is the transition equation that governs how the land per capita changes depending on land per capita today and fertility level. Okay, so regular dynamic programming problem, no particular difficulties, but let me pause here. So if you have questions, very quick questions, I can answer them. Otherwise, we're gonna take a break and continue at 9:55. Any questions?
No, thank you.
All right then, so let's meet at 9:55 after the video conversion and continue discussing these economies. All right?
Okay.
All right, bye-bye.